So today's lesson, we're going to investigate a more exact way of solving systems, but there are two warm-up problems for you to do by the graphing method, which we learned last class. So I'd like for you to go through this system. We have 3x plus y equals 8 and y equals x minus 4, and I want you to estimate its solution by graphing. If you need to, you can check your work. Well, you should always check your work by using your calculator. And remember that you can graph both of your equations in your calculator and then type menu, analyze graph, and then intersection. Then select your lower and upper bounds, and that will allow you to confirm that your intersection point is correct. So go ahead, graph this problem. When you pause the video, when you click play, we'll check together. Okay, so you have now graphed both equations. You should have isolated your equation up here and gotten it into slope-intercept form, giving us y equals negative 3x plus 8. So that's what I have down here. Graphed both and then found the intersection to be the point 3, negative 1. So remember, we write our solutions as points because the solution to a system is a point. We have one more to practice. So take a moment, work this one out. If it's not a clear intersection, then use your calculator to find the more exact intersection of the system. All right, click pause, and when you click play, we'll check together. Okay, so for this one, you should have isolated y, which means subtract x from both sides. Then you're left with 3y equals negative x minus 21. Then divide everything by 3, giving you y equals negative 1/3 x minus 7 for this second equation. Then you should have graphed both equations and noticed that it was not a clean intersection here. The points did not land on top of each other as you were plotting for your lines. Therefore, you should have gone to your calculator, graphed both equations, and then found the intersection of your two lines by typing menu, analyze, intersection, lower and upper bounds, and you see this point comes up. Now remember, it's probably been rounded, the point the calculator gives you. So we will give our answer, we will copy that point, but use the approximation symbol in front of it just in case it was a rounded point. All right, so that's just a little review and practice with solving systems by graphing. So today we're going to explore solving systems by substitution. So instead of graphing, we can actually solve for x and y, and you'll find that this is often quicker, and we'll always give an exact solution rather than an estimate, especially when it's not a clean intersection. So we need to remember that x and y are the values of the point that actually make both equations true. So if you remember in the graphing lesson, I showed that if you got, for example, your solution to your system was the point 2, negative 2, let's pretend. This 2 is your x value, and the negative 2 was your y value. And so what we looked at is if we replaced every x in both equations of our systems with 2 and the y's with negative 2, we got true equations for both equations if that point actually worked out. So we can solve for these x and y values individually. Now in class, I'm having students just play around with the following system, y equals 5x and 2x plus 3y equals 34, to just see if they can figure out a way to solve for x and y to get solutions that work for both. But since we are just making a video right now, I'll go ahead and go through the process and then show you how to do that problem with these steps. So step 1 is to solve one of the equations for a particular variable. You get to decide here if you want to isolate, and I will write that down because we're really isolating these equations for either an x or a y. You get free choice here. You get to decide what to isolate one of your equations for, and I'll show you that it doesn't matter which one you isolate for. Once you do isolate an equation for one of those variables, you will then take what that variable is equal to and substitute that into an equation for that variable in the other equation. So what's really important is that you go into the other equation. If you isolated on the first equation, then you substitute what you isolated for into your second equation. Lastly, once you get the value for your variable you were solving for, you will use that, substitute it in, solve for the other variable, and that should create your point. So let's look at this. It's often easier to just look at it mathematically rather than all in words. So step one is to solve one of the equations for a particular variable x or y. So notice in this system that y is actually already isolated. It's already solved for. Y is completely by itself. And we see that y is equal to 5x. So step one is done. Already done for us. So if we've got y isolated and y equals 5x, what that means is that this y and this y should be equal to each other. So if this y is equal to 5x, that means that the y in the other equation should also be equal to 5x. So what we'll do is recopy the second equation, but instead of y, we're going to replace it with 5x. Because we see that the y should be equal to each other. So they should be equal to the same expressions as well. So from here, the beauty of that step is that now we just have one variable all the way through our equation, and we can now solve for x. So 2x plus 15x equals 34, and now all I do is combine like terms and isolate my x. So x equals 2. All right, that was step 2. So we are now almost done. We've got the value of x that works for our equations, but we need to now find the value of y. Once you get x's value to be 2, x should be 2 in either this equation or that equation. It's equal in both equations. So that means that you can pick which equation you substitute 2 into. If you choose the first equation, you can see this is kind of a cleaner equation, a simpler equation. There's not as much to do. So I would recommend putting 2 into that one, but it's certainly not wrong to put 2 into this equation, the second equation, and solve for y there. Just make your life as easy as you can. So here, y equals 5x is the simpler equation. So instead of y equals 5x, I'm going to replace x with 2 because we found x to be 2, meaning that when we simplify, we figure out that y is equal to 10. So we now have the values of both coordinates for that point. Lastly, it is very important to remember that we are solving for a point of intersection. So you are not done until you write your x and y values together as an ordered pair with parentheses. And the thing that's special about this point is that I can put 2 in to the x in the first equation, and I can put 2 into the x in the second, and I can put 10 into the y in the first, and 10 into the y in the second. And when I simplify both of these, I get true statements. So 10 equals 10 works, and then 4, this is 4, plus 30 is 34. That one works too. So we know we've got a correct solution. Let's practice another one. So we have this system here, and we want to solve for x and y to make that ordered pair that would represent the point where these lines would intersect. Step 1 is to isolate one of the variables, and we get to pick. We could isolate this x, this y, this x, or that y. That choice is ours. What I'm going to recommend is that you try to make your life easy, though. Notice that this x has a coefficient of 1, so it's almost close to being isolated already. And this y is also pretty close to already being isolated. So what I would recommend is choosing one of those to get by itself, because it's just one quick and easy step to get those either of those fully isolated. So I'm going to just choose to isolate this x, which means all I have to do is add 5y to both sides. When we do that, we get x equals 2 plus 5y. And now I'm done with step 1. Once I get x to be equal to 2 plus 5y, I'm going to take that expression and put it in for x's value in the other equation. Remember, I started by isolating my top equation, so now I go into my bottom equation. So I'll recopy this 2 and then open parentheses and replace the x with 2 plus 5y. Now I bring down the rest of the equation, plus y equals 4. To solve for y, I need to distribute. Combine my like terms, so this is 11y. Divide, and 0 divided by 11 is 0. So we get y's value to be 0. Once we find out y's value, we can put 0 in for y in either equation. I do recommend that you go back to an original equation, so one of the ones typed, because that one has not been worked with. There's less room for error there. So again, the choice is up to you. Let's just put the y of 0 into the first one. So the first equation was x minus 5y equals 2. So instead of y, we're going to replace y now with 0 because we know y's value is 0 because we found it here. So negative 5 times 0 is 0. So x equals 2. Finally, x is 2, y is 0, so your point should be written as 2, 0. And that's your solution. All right, remember that to check the solution, you can put 2 in for x in both equations and 0 in for y in both equations. And if you get true statements, then you know that you've done it correctly. This one's pretty easy to check in your head, but sometimes you'll get solutions that are fractions or not as pretty to look at. So what I wanted to remind you is that on your TI Inspire, you can check your solutions by storing your values for x and y. So once we do that, then we can type in both equations and confirm that we get true for both, and that will show us that we have the correct solution. So let's quickly do that. So we got x's value to be 2, so I'm going to go to my graphing scratch pad and type 2 and then control store as x and hit enter. And then I'm going to store y as 0, so 0 control store as y and hit enter. So now I've stored x is 2, y is 0. And we're going to now check that x minus 5y actually does equal 2. So you'll just type in x minus 5y equals 2 and hit enter. You should get true if you've done it correctly. You can't stop there though because you need to get true for both. You need to make sure 2 and 0 for y work in the second equation. So now we'll type in 2x plus y equals 4. Oops, 2x plus y, oh my goodness, equals 4. And now that I see I've got true for both equations, I know that my solution is correct. That is the point of intersection. All right, let's look at a couple special situations that may occur. Let's solve this system using substitution. Step 1 is to isolate a variable. Hopefully you see that the y is already isolated, so that is very convenient for us. So we'll replace that expression in for y in the first equation. So 6x minus 2 times, now I'm replacing y with 3x plus 2 equals negative 4. I need to distribute. And here when I combine my like terms, 6x minus 6x goes away and it's 0. And I'm left with negative 4 equals negative 4. If you notice that your variables go away, but the statement you're left with is true, this represents a special scenario. So if you'll remember, our systems can have one solution, no solution, or infinite solutions. If your statement that you get when variables disappear is true, this is an example of a system that has infinite solutions, meaning that these are actually the same line. So if you were to convert this top equation to y equals mx plus b, it would convert to y equals 3x plus 2, just like the bottom equation. So you actually have the exact same line. So while you may not have seen it right from the beginning, if when solving your variables go away and you're left with a true statement, then you have infinite solutions. And you would actually you still need to write infinite solutions as the answer. Okay, and for this last example, again, we already have y isolated, so let's replace it into the top equation. Put parentheses around the 2x minus 3 that you are replacing y with, because we need to distribute that negative. And again, 2x minus 2x, that goes away, so we're left with 3 equals 8. Now this time, this is not true, this is false. 3 does not equal 8. So this is an example of parallel lines or no solution. So if you were to convert both of these into slope-intercept form, they would both have the same slope but different y-intercepts, making them parallel lines. And again, we can't quite see that or tell that from the beginning, but in our solving, if that situation occurs where you get a false statement, that implies that your lines were parallel. They would not intersect, so there is no solution. There is a challenge problem at the end here. If you feel ambitious and want to try this one out, we're going to be dealing with some fractions, which makes it a little more involved. But if you want to play with that system, solve for x or y first and then find the other variable's coordinate, go ahead. You can click pause, work this one out, and then when you're ready to check, hit play. Okay, so if you have worked this one out, you should be getting 170 41st, comma 115 41st as your x and y values that represent the point where your lines intersect. So this one just had a little more work because when you isolated either of the variables, you got equations that had some not so fun fractions to deal with. It doesn't mean this was not possible to solve. It just meant we probably had a little more work to do than some of the other ones we've seen today. But that is solving systems by substitution, and we'll conclude our lesson.